Good morning. Hi, Chris.
Morning. How are you?
I'm good. We finally got some rain.
Yeah, a little bit today.
Just a little bit. Is it done for the day?
I hope not.
I heard it wasn't going to be much.
Yeah, it doesn't look like it.
A tenth of an inch or something.
It's gray and wet up here, but not much is coming down.
Yeah. I woke up in the middle of the night to the sound of rain. That was pretty good. First time in what, 3 months? 2 months?
It's been a while.
Yeah. Well, it's a big day today because we get to see how the debugger works. Finally, huh? Oh, let me clean up my computer a little bit. I mean, I got to close all these little windows and stuff. Close. Close. There we go. So I had a couple of things planned for today. First was to show you how to use the interactive debugger that's built into our IDE. And second was to show you some of the string functions that are built in to the standard library. In the previous weeks, I've shown you some string functions that we just made ourselves, just to show you kind of how strings work, but there are lots of built-in functions, and I'll show you some of those today. One announcement, though, is on Thursday, we will not have our usual live stream that day. We're actually interviewing for a new full-time position in our department, and so I'm going to be off that day, spending time in Zoom, interviewing people remotely. It's the first time we've ever done that, interview people over Zoom, and so there won't be any live stream that day. So I'll be tied up from like 8 a.m. until 3 p.m. that day. We will just kind of catch up with the live stream next week. Any questions before we begin? So we're about halfway through the semester. It's just flown by. This is week 8. So I know some of you probably have midterms this week. We don't have any exams in this class. It's all just programming assignments. But by the end of the week, I should have a survey up for you to fill out. That'll be a survey to just kind of check in with you, see how you're doing, see how many assignments you've completed so far, and just kind of remind you that, you know, you need to, if you've been kind of putting off doing some of the assignments, you need to kind of pick things up a little bit. I have been working my way through the assignments as well, so you've probably seen some notifications come through on your account that I've marked things complete or I've given you feedback. One thing to keep in mind is that if you haven't turned something in and the soft deadline for it passes, then the system automatically gives you an incomplete on it. Mostly just to remind you that you didn't do the assignment. You probably need to do it soon. It by no means indicates that you can't change that score. Of course, you can just turn in the assignment and then I'll take a look at it. But I've had a couple of people send me an email saying it's marked incomplete, but they turned it in. What's the deal with that? And the answer there is it just marked you incomplete automatically, and then I need to go through and actually look at your submission and then change the score accordingly. So it'll still note that it's incomplete until I get a chance to look at it. Until then, it'll remain incomplete, and if it does, I will give you a notification that maybe there's something you need to improve on it, or I'll mark it complete. So if it says incomplete, but there's no like feedback on it, then it means I just haven't looked at it yet. I wish there was a third option, which was like not graded yet rather than incomplete, but there isn't. Okay, so what I have here on this, this is doing it again, where you can't see the camera. Let me see, if I switch back to this, you can see that. But if I switch here, oh, you can see that. But that's blank. Oh, that's weird. Hold on. Let me see if I can fix that. Wow, that's bizarre. Let me see. Try that again. Oh, there it is. That's weird. Okay. Sorry about all the switching. That's just weird how it sometimes does that. It happened to me yesterday in the other class where they could see my face, they could see the laptop, but then I switched it over the iPad and it was blank. And then I had to reset some equipment in order to get that to work. But apparently it's working today. Okay, so what I have here is a little program that I worked up last night. And this is not intended to be the solution to the CSI assignment, but rather it's kind of like a little simulation of the assignment. I have a method here, a function here called save jpeg. It takes the same parameters as the one that's built into CSI, but it doesn't do anything other than just print out what file name it is saving to. And then in my main, I have a start, which starts at 0. I have an image counter, which is counting up the number of images that it is saving. And then just as a simulation of the way the program works, it starts at 0, goes up to 10,000, and increments by 500. I've got a string here to hold the file name. And initially, the end is equal to the start. And then I simulate finding the end of the image by just incrementing end by 200. Of course, there would be a loop in there to actually find where the real end is. And then I use sprintf here to build up the file names. So it's built out of a 3-digit number, like 007, and then dot, and then jpg. It puts in the image number into that string, and then it calls save jpeg. And remember, save jpeg in this simulation here doesn't do anything other than just print out the file name that it's printing out, that it's saving to, and then increments the image number. And so the reason why I cooked up this little program was because I had someone write in and said, this is basically what my program looks like, but when I run it, I get a weird behavior. Let's go ahead and compile this. I call this Debug Me because we need to find the bug in it. And it just says here, saving to 001.jpg, but it starts out with 000. So it seems to be incrementing, but then once it gets to 1, it just stops. So what's the problem here? And I eventually did figure out the problem, but my purpose here is to show you how you could use the debugger to figure out maybe give you some clue as to what's going on. So this is kind of unusual behavior here, where it just goes 0 and then 1 and then it stays at 1, even though we're incrementing this number here. So maybe, of course, the first thing you might look at is this loop actually running? Like, is it not actually, is it maybe going to the loop once and then stopping? But if that's the case, why does it eventually stop printing things out? And why does it print out like about, I guess it's about 20 things or so? 10 or 20 things? Now you might look at this code and maybe this happened to you and you look at it and go, I know what's going on. But let's see if the debugger can help us out with this. If you've used a debugger before, you'll probably be a bit familiar with the user interface on it. I guess the first thing to remind you is that debuggers do not remove bugs from your programs. They just help you find them by helping you to look at your code as it's running and look at the various things like variables. As the program goes line by line, you can see the values of the variables changing. So in order to get the debugger working on our IDE, you first need to install an extension to get it to work with the back-end debugger, which is called GDB. GDB is actually a command line tool that is used to debug programs, and you are going to install an extension into our IDE that hooks those two things together, hooks in the back end with the front end that you can see. So to do that, go over to our extension manager, which is this icon over here. And then if you just search for debug, which I've already done here, I'll just do it again. Search for debug. The very first one that comes up is called native debug. And this is what we want to install. So just click on install. And it's going to download the extension and load it into our IDE, and now it's ready to go. So the next thing to do is to click on the debug icon, which is over here on the left. And as it is, nothing's going to happen when you click on this green run button because we haven't configured the debugger. We haven't told it how to run our program. So right here in this pull-down menu where it says no configurations, select add configuration. And it should open up a window over here along with some options, a pull-down menu. So we're going to select GDB Launch Program. Okay, if you didn't see that, let me close this. We're going to click on Add Configuration. It's going to open up this window. You're going to scroll down and find GDB Launch Program and select that. And that'll kind of fill out some of the values in this configuration file. And there's two things essentially we need to change here. One is we can change the name of this configuration so that in this pop-up menu something appears here that makes sense to us. So we could change this into like debug a.out. And then for the target, you type in what you would have typed in order to run your program, which is ./a.out. I'm going to save it, and now we have debug a.out as one of the configurations that we can select, and then we'll click on this green run icon. And the program runs, and usually there's some output here that we can see. Where did that go? Not here. Let me try it again. Oh, I saw it really quickly. It flashed by. Let me close this. Well, it went really fast. In the past, that output usually stayed up on the screen so that we could see it. So I'm a little confused as to why it's not appearing. So if you want that debug console to appear again, you just click on this button right here. It opens up that. Now I'm wondering if there's a configuration option we should have put in that was like, don't clear the screen when you're done. Well, anyway, let's ignore that for now. And let's, because the whole program just ran and flashed by on the screen, let's have it stop at some lines of code so that we can see what's happening as it's running. So we're going to go back over here to our Debug Me, and if you scroll your mouse over here on the left-hand side, you see these orange dots. And you can click on one of those, and that'll set what's called a breakpoint. It'll tell the debugger to stop when it hits that line, and then let you inspect the values of variables when that are current at that line. So it would be a good place to stop this program to find out what's going on. Well, why don't we stop it maybe like now. This one here is disabled because this line here is not an actual line of code that can be executed. A declaration of a variable is not a line of code that can be executed. So it's not letting you click there. But maybe let's stop right here at line 15. So I'm going to click on that. I have a breakpoint now set at line 15. And if I click on run or start, now I have no idea if it actually stopped there. This is a little embarrassing that it's not working the way I expected it. Let me close this. Did it do the whole thing? Should not have. This is terrible. This is why I should have rehearsed this before class today. I was like, this is going to work. I don't have to rehearse this. I know how this works. And then now it's not working.
So I was having the same problem.
Yeah.
And it looks like you have to, when you compile the program, you have to add a parameter, the -G flag.
Yeah, but I wouldn't think that would affect its debugging. But you're right. When you compile the program, you do need to add a flag to it. That's the -G. Little. Is that the one you added?
Yeah.
And that flag tells the compiler to insert into the executable just little markers to let it know what instruction in the executable corresponds with which line of code in the source code. Let's try running this again. I'll go over here. Oh, you're right. Now it's stopping. That is good. So I guess that flag is necessary just to get the debugger to even work. My experience in the past is if you didn't put that on there, then all it would do is just run the program but not show you that things like names of variables or names of methods. It would just show you addresses. But apparently this is needed just to get the debugger to even function. So when you compile your program, put in that -G flag, and then that'll tie the executable to your source code and let the debugger work. So at this point, it has stopped here at line 15. What this means is that it has not yet executed line 15. It has actually stopped just before it hit line 15. And now if I tell it to go to the next line, it will then do line 15. But we can, at this point, inspect some of the variables. If I click on variables here and then roll down local, I can see what these values are. I can see that end has a value of, what is that, about 4 million. Start is 0 and IMG is 0. So are those values that we would expect to see? Whenever you're debugging a program, you always need to match up, or not match up, you need to make a prediction about what you're supposed to see and then look to see if that matches your prediction. And if there's a mismatch, then either your prediction is not correct or something's wrong in your program. So debugging is a skill to pick up where you need to kind of act like the computer in your head. What is the computer supposed to be doing? And then you look at reality. What is the computer actually doing? And if those match up, then that's probably good. And if those don't match up, then you need to figure out why. So looking at these values, is 4 million and something for end what I would expect to see? Is 0 what I would expect to see? And is IMG also 0 what I would expect to see? And I think there the answer is yes, because I have set the value of start to be 0. I've set the value of image to be 0, but I have not yet assigned to end. So it has a garbage value at this point. To go to the next line, there are two options. There is step over and step into. Most of the time, there's no difference between those. It's when you're calling a function like sprintf or save jpeg that these have different behaviors. If you do a step over, it'll go to the next line, but it'll go in. Let me back up. If you do step into, the next line it executes when you call something like save jpeg is to go into that function and then stop. If you do step over, it'll call the function and return from the function and then just go to the next line in main. So for example, if I want to go to the next line from 17 to 18, I would use a step over because I really don't want to go into the sprintf function. I'm pretty sure that works correctly. But if I was trying to debug, let's say, the save jpeg function, I would want to step into that one so that the next line that it would stop at would be in the function and I could see what's going on. So right now I'm just going to use one of these two because I want to go from 15 to 16. So let's just let's do step over, and we can see now it has advance to line 16, the value of end has changed to 0. When I do the next step, what would I expect to see here in these values? I see 0, 0, 0. When I click on step, what would I expect to see? Should I see any of these change?
You'd expect end to change.
Yes, because this line here should be changing end by 200. So if I click on step over, I would expect to see this change to 200. And it does. So it matches my expectation. Now I'm going to click on step over because I don't want to go into the sprintf function. And now we're on save JPEG, and I'm not entirely sure that that one is working correctly, but let's take a look at the value of fname here, file name. So I'm going to click on this arrow here, and we can see that it is 000.jpg, which is what I would expect. My image number is 0. And so the string that sprintf puts into that string, puts into that variable should be 000.jpg. So that looks okay. So at this point, I should start kind of developing some hypotheses as to why my programming is behaving the way it does. So one hypothesis is something's actually wrong with save JPEG. Even though the value of the string is like 005.jpg, for some reason the save JPEG function is printing out the wrong file name. So let's explore that hypothesis. We need to come up with some kind of evidence to either prove that that is correct or disproves it and shows that that's not correct. So our working hypothesis is something's wrong with save JPEG, and it's just printing out the wrong thing. So let's use step into, and now we come up to line 5. And we can look at the variables inside of here. We can see that s is 0, that's the start value. Length is 200, that was the end value that was passed in. And the value of file name is 000.jpg. So that all looks okay. Let's do step over because I don't want to actually go into printf. And let's see what came out. Did anything appear? Of course not. Let's keep stepping. So we'll go back over here. We're going to increment image. So if I do a step over, I should see the value image be 1, so that's good. Now I'm at the top of the loop. So if I step again, I see end is 200. And now it's 500, okay, because the value's been copied. Now it's 700. The value of fname is now 001, so that's good too. And then let's go into save JPEG, and we can see the value of start is 500, length is 200, the file name is 001. Still don't see any output down here, but we'll figure that out in a little bit. Let's keep stepping.
Do you have to switch to the terminal tab?
No, terminal is completely independent.
Okay.
So the debug console is its output, and the terminal is separate from that. Okay, so at this point, we should see the image number. Oh, wait a second. Is this right? Wasn't this 1 before? And now it's 0. Well, let's just, maybe I'm not remembering things. Let's go ahead and we'll increment that to 1. Okay, let's step. Okay, start is 1,000. That's good. And then end takes on the same value. Now end should be 1,200. And then we call sprintf, and we can see this now. Wait a second. Did you see that? Wasn't this 1 just a moment ago, and now it's 0? So if I step over this and increment image, now this is 1 again, so image is 1. And then I come back into the loop. The value of end is 1,500. Okay. Now end is 1,700. And then I'm going to call sprintf. And then look at that. The value image changes 0. So something's going on in the sprintf that's causing the value of image to go to 0. And so that would explain why the output of my program is just a bunch of 001s, right? It looks like the value of image is not incrementing correctly. It's going back to 0. And so now we got to figure out, why is that happening? Because I don't see anything wrong with the code. I don't see any reason why calling sprintf, which has, I mean, the only thing that sprintf has anything to do with the image is here, right? But I'm passing in its value. I'm passing in a copy of it. So it's not like sprintf should be modifying the value of image, but apparently it is. So we have a new hypothesis. It's not save JPEG that's printing out the wrong thing. It's that something is going on inside of sprintf that's causing the value of image to be altered. Could there be a bug inside of sprintf? I mean, I suppose that's possible that there's a bug in there, but how likely is that? I mean, sprintf has been, in use for decades. For us now to have stumbled across a bug in it, I mean, I suppose, maybe, but it seems unlikely. So what's going on there? So here's where we really have to start digging around. I mean, let's assume there's no actual bug inside of sprintf. It has something to do with the variables. Now again, if you see the error, don't spoil it right away. But if you don't see the error, where would you go and start poking around? How could you figure out what's going on here? I mean, we literally were watching these variables over here, and when we called sprintf and returned from it, this value popped back to 0. What is going on? Any ideas? Chris, you're shaking your head. You're like, I have no idea what's going on. Or do you see it? Mary, do you?
I don't see it yet.
You don't see it, Mary? Do you have any idea? What was that?
Not yet.
No?
No.
This one's definitely a stumper. I mean, really, I had to look at this one for a while before I figured out what was going on. It's weird. Okay, so the suggestion is before the sprintf, print out the value of image, and then after the sprintf, print out the value of image. And let's just see. Now, I mean, it should match what we see over here on the left-hand side, but let's go ahead and put those in. So I need to come back here, and we're going to edit this. Now, I mean, there's always a risk to printing out a variable because we think there's something going on inside of sprintf. So we're using printf here, and almost any time you instrument or produce some log messages from a bug like this, there's always a risk that putting those statements in are actually going to cause the bug to go away. I've seen that happen, that just the mere act of printing things out causes the bug to disappear. So we have to be a little careful with that, but let's press ahead and see if that helps us or actually hinders us.
I do see something now. I don't know if it's the cause, but yeah.
So let's print out before and after these two values, and let's just do it from the command line and see if that tells us anything. So before we called sprintf, it was 0. After it was 0. That's what we expect it to be for the first iteration. Then we saved to 0, 0, 0. Before it's 1. After it's 0. So we're saving to 0, 0, 1. So right here, this is not correct, right? This should be 1 and 1. This should be 2 and 2. This should be 3 and 3. But it's 1 and 0. So very definitely something's happening in this sprintf that's causing the value of image to go back to 0. So let me delete these here. And the reason I'm deleting it is, again, I don't want those printfs to somehow affect what we're doing. We did see that it is exhibiting the same behavior that we saw before, which is the value of image is somehow changing in the sprintf. So since I've recompiled this, I probably need to stop this debugging session and restart it. So I'll have to tell you that debugging this particular example, you're probably not going to get it just by staring at the values of the variables. There's clearly something else going on here, so we're going to have to dig a little bit deeper. We're going to have to see actually what's going on inside of the computer's memory in order to figure out what's happening here. So in order to do that, what I need to do is actually see how are the variables being laid out in the computer's memory. I can see their values, but I can't see where they physically are in memory. So to do that, I can do that. Let's see, is there a way for me to just, what I can do here is I can come down here. And this is essentially the command line interface to GDB. Remember I said that GDB is a command line tool. We are putting on top of it a nice, easy to use graphical interface, but behind the scenes, it's just a command line tool. And so this command line prompt down here gives us access to that command line. And so there are a bunch of commands you can type in, and one of the commands is print. And then you can type in an expression here, and it will evaluate the expression and tell you the result. I mean, I can do 3 plus 4, and it will tell me the value of that expression. This expression number 1 is 7. Okay, that's not terribly useful, but I can do things like, I can say print the value of start, and it tells me the value is 0, which matches what I see up here. And I can say print the value of end, and it says it's 4 million and something, which matches what I see over here. But I can also do things like print the address of start. And it tells me what the actual address of start is. And we can see that it is a relatively big number, so it's high up in memory. That tells me this is on the stack, which is what I would expect. And if I print out, let's say, the address of end, it tells me that one as well. And I can do that for all of my variables. Let's print out, what other variables do I have? I have image, and I have fname. Is that it? Are those all my variables? Okay, so let's write some of these down. Now, I'm not going to write down the whole address. Really, the only thing I'm concerned about as far as telling these apart would be maybe just to look at the last 3 or 4 digits of this. So let me write these down. I have start is at B08. End is at AF8. Image lives at B04. And fname lives at AFD. And all of these have an E in front, right? So that's not changing. So let's try to map these out. Let's try to draw a picture of where these things live in memory. Which of these comes first? So you look at these numeric values. Which one comes first? So it's probably the one that has the A here. So we've got AF8 and AFD. So AF8, the 8 comes before D. So end is actually first. So here's end, and it lives at AF8. Okay, and then fname comes next. It's AFD, and remember fname is 7 bytes long. It's a 7-byte string. You can see it right here. Oops, covered up by that 0. Right there. So 1, 2, 3, 4, 5, 6, 7. AFD is where fname lives. And then we have B04 and B08. And B04 is IMG, and B08 is start. And I think one thing that's kind of curious about here is look at the order in which these variables are declared. We have start first, then image, then fname, and then end. So it's start, image, fname, end. And then look at the way they're arranged in memory. They go backwards. Start, image, fname, end. And the reason for that is, remember, this is a stack. And the stack in memory is building downwards. So start is the first thing that's added to the stack. It actually goes kind of like, up here. And then image, which was the next variable declared, goes right below that. But below that means next on the stack. And then file name comes next after that. And then end is the last one that's pushed onto the stack. So although they appear to be going backwards, in memory, they're actually laid out according to the order in which they were pushed onto the stack. Are we good so far? So we can see, let's move this ahead by 1, so the value of n is something reasonable. We can see here that the value of end is 0. So there's 0 here. The fname right now hasn't been written yet, so its values are just a bunch of garbage. But the value of start and image are also 0. Then we're going to advance this So now end is actually 200. Let me change that. So this is what it looks like now. I just crossed this out. And then we're going to call sprintf. So the value of f name is 000.jpg. So we have 000.jpg. Okay, and then we call save JPEG, and then we increment image, and now value of image is 1. So this is no longer a 0, this is now a 1, and this is what our picture looks like. Okay, so the value of end is 200, the value of image is 1, the value of start is 0, and the file name is 000.jpg. Okay, let's increment some more, or let's step some more. So now the value of end is still 200. The value of start is now 500. And you see what I'm doing over here in my picture is I'm keeping track of these variables in this drawing so that I can see what's happening. Okay, so the value of end is now 500. So I just updated my picture to reflect that. And now it's 700. I just clicked on the step. So now it's 700. So I need to update that again. I guess I'll just cross this out and put 700 there. And then I call sprintf. So the value of the file name is 001. That's correct. So you change this to a 1, but the value of image has gone to 0. So that's a problem right here. This should have stayed a 1, but this went back to 0. Now, Chris, does that match your expectations of what's happening? Yeah, so you think you know what's going on?
Yes.
Okay. Does anybody else think they know what's going on here? Is there anything, now I'll have to admit, is there anything intentionally a little misleading about the drawing I put here? This sketch I've done, is there anything like I've drawn in there that's not quite accurate? This is where attention to detail really comes in. What didn't I do, or what did or didn't I do? So what I did when I wrote in the file name here is I really didn't show the individual bytes. I just scribbled the name in. If I was to show the individual bytes in there, it would look like this. 001.jpg, right? And where does the null character go?
Goes right after the G.
Goes right after the G, but where is right after the G? Well, it's overlapping with the image variable. So that null character is being written here. And that's overwriting the value of the image value. So that null character, whose value is 0, is going in where image was and changing its value to 0. So it's the way the values are being laid out in memory that's causing the overrun on that string. The string is only 7 characters long. We actually need a total of 8, at least 8, to hold the file name. 3 for the digits, 1 for the dot, 3 for the dot, the JPG, and then 1 more for the null character. This is a really common error to do, is to set your string to be too short. You figure you only need 7 characters, but you actually need at least 8. I would almost always overshoot that a little bit. I need at least 8, I'm going to make it 10, right? Or 12 or 16, just to make sure I don't run into any problems. So let's go ahead and change this to 8. Save it. We'll recompile the program and then run it. And we can see now the problem has gone away and it's incrementing correctly. So let me put this back to 7. And this actually brings up another issue, which is, I mean, I can see now that it's overwriting the value of image, but why? If I look at the picture, it doesn't quite match up. I mean, after all, the value of image here is, it's 1, right? And this 1 is like over here. Right? You can think of this as being like 0001, although it's 32 bits wide, right? So it's really a whole bunch of zeros and then a 1. But why is this null character overwriting the 1 when the 1 is way over here? And the answer is it's not. It's not really over there. See, the Intel processor stores the individual bytes of a multi-byte value, like an integer, in reverse order. A byte is made up of, an integer is made up of 4 bytes. But they're stored in reverse order, so the least significant byte comes first, and the most significant byte comes last. And you might ask, why is that? That doesn't seem to make any sense, right? You know, when I see the integer here, I want the least significant byte to be over here on the right, and the most significant byte to be over here on the left. Why is it all switched around? Well, from a memory perspective, remember, this is the lower address. The least significant byte is stored in the lower address, and the most significant byte is stored in the upper address. And so from a memory layout point of view, that makes total sense. The least significant byte is in the least numbered address, and the most significant byte is in the most numbered address. It's just a sort of what's it called, a quirk of the way that we draw things out, that they end up being reversed. So it's actually not the memory layout that's reversed, it's our drawing that's physically reversed. We tend to put the least significant byte over here on the right, but actually, from a memory layout point of view, it's on the left because the lower number addresses has the least value of the bytes. So Intel processors are what are called little endian, which means the little end comes first. And this is not actually like a racial slur. This is actually from the book Gulliver's Travels, in which he meets the little endians and the big endians, and they're named that because of the end of the hard-boiled egg that they eat first. You know, the little endians crack the little end of the egg, and the big endians crack the big end of the egg. And so Intel processors are called little endian because the little end, the least significant byte, comes first. And other processors like, I'm trying to think. I know that the Motorola processors, which were used for older computers like the 68,000 processors, those were big endian processors. So the big end came in the lower number addresses, and the least significant bytes came in the upper addresses. So it's almost like they were written out in memory the way you write them out on a piece of paper. And now I'm curious, what is ARM? ARM is used for things like iPhones, Android phones, pretty much everything else these days. I'm just curious, is ARM a little end or a big end in processor? ARM, little endian. Is it little endian? Let's see. Yes, ARM is also little endian. So the answer there is, although it appears the 1 is actually over here, the 1 is actually being stored up here in the least significant byte, or the least numbered byte. And so that's why this null character is overwriting that 1 with a 0. And so there's our answer. And we had to figure that out, not by just looking at the values of the variables, but by seeing how they're laid out in memory. So when you're using the debugger and you're stepping through the lines of code, and it seems like some weird thing is happening that shouldn't be happening, then you might have to dig into how the memory is laid out. Otherwise, the debugger can help you just fine by just looking at the values of the variables and stepping through your code one line at a time and just watching the values change. So as long as there's no weird memory collision that's happening, you can just watch the values of the variables and then hopefully see where your problem is. In your debugger, you can do things like you can set conditional breakpoints. So you can stop when a line hits a certain line of code, or when it calls a certain function. We could say save JPEG right here. We could say stop whenever we call save JPEG. We can also do a conditional one, like stop when the value of image is 15. And so we'll just run the program and keep running until the value of image is 15, and then it will stop. So that will allow you to basically march forward in your program until you know that a problem occurs when, let's say, the value image is 15 or more. Oh, that's not going to work because I misnamed it. Let's see. Let's remove that one. Let's try this again. Add a new breakpoint. Save JPEG. Well, maybe I'm not using this correctly here. Let's remove this one. You can also put in watch expressions. So instead of just watching the name of a variable, you could have it plug a variable into a function and see what the value is. Or you could use it to maybe concatenate two numbers together or two strings together and see what its value is. So you can actually construct an expression and then watch those expressions change as your program is running. Okay, so that was a quick introduction to the front-end debugger. Do we have any questions about that? Akash says, that was an insane bug. Yeah, it took me a while to find that one. But now it's one of those things where I file that away in my toolbox of things to look for. And then when someone shows me a program and says it's behaving strangely, that now, among several other things, is one of the things I kind of like pay attention to. Like, are your strings actually big enough to hold what you're supposed to be holding? That I think just comes with years of experience debugging student programs. Is now I have this mental list of things I look for. And I don't know, a lot of students are kind of astounded that I can walk up to the program and go, there's the problem right there. Because I'm just usually when I'm in a classroom, they're sitting at their computer, and as I'm walking up to the computer, I'm already scanning through their code visually. And for some reason, again, after years of doing this, minor problems to me just like stick out like a little red light. Like sometimes it could be a parentheses is not closed, or you're missing a brace, and it's weird for me. Those just like stand out. It's like it's obvious, and I think it's just because my brain has seen code so much. It knows what properly indented, properly structured, properly constructed code is supposed to look like. And when it doesn't look like that, my brain goes, that's a red flag. And so it's like when I see a missing It's like I know a brace is missing, right? Because the braces don't look quite right. If they're lined up correctly, I don't know. I can't really describe it. How I can sometimes just walk up and just know instantly where the problem is. You will develop that hopefully over time as well, that you'll have seen the same problems over and over again to the point where some of those things just stick out and they're easy to fix because you've seen them before. This problem with strings being too short, I've seen that often enough before that that's one of the mental things I just look for. Are your strings long enough? Is there space for that null character at the end? Okay, so that was a quick introduction to the debugger. I hope you got something out of that, but at the very least, you got introduction to how to install that debugger and how to run it. And I need to work on why isn't the debug console printing out the lines of code as I run them. I vaguely recall, very vaguely in the back of my mind, recall somebody last semester found a fix for that. It had to do with this configuration. They were able to add something to this and maybe fix that problem. So I need to work on that. And see if I'll probably look back through my videos from last semester and see if I can find that little tip that someone brought up. Okay, so a little bit about string functions. Oh, there's a question here. What if we made this 6 instead? So it's just way too short. So that every time we called sprintf, it overwrote even more stuff. It's probably not going to cause a core dump. You're only going to get a core dump really if your program steps outside of the segment boundaries. But in this case, it's not doing that. It's just overwriting a variable that's sitting right next to it on the stack. So you're not going to get a core dump, but you will probably get really weird behavior. I'm curious. Let's see. Let's run this. So I changed it to 6. Compile it. I run it. And oh, we get 104.jpg. Why 104? Let's make this 5. Now it goes 0, 26,000, and then 1.7 billion, and then it stops. But why 104? Oh, you got it. 104 is the ASCII value of G. So that meant the G was impinging on image right there, and its value was right there. That's where the 104 comes from. Now, as to why, when I made it the value, when I made that string 5 bytes long, why the numbers just went absolutely crazy at that point. Well, you know, obviously they were going way over inside of image here, and so the value of this was now changing by quite a bit. And let's see. We'd have to map it out in memory in order to figure out exactly why the numbers were going crazy. Okay. So switch gears a little bit. C has a bunch of built-in string functions. We rewrote some of our own, what was it, last week, or week before last? But let's see some of the ones that are built into the standard library. So to use these functions, you need to include string.h at the top of your program. There's no other thing to link in. You just need to include this header. And there are about a couple of dozen or so string handling functions. Here are the most common ones. The first one, if you want to copy one string into another, the function is strcpy, string copy. You give it the destination string first and then the source string. So it's actually a little bit backwards than what you would expect. So with all of these string functions, you have to pass it in an actual array of characters. Okay, so the memory already has to be set aside for these string functions to work. They will not create strings for you. So destination needs to be an array of characters. Source also needs to be an array of characters. And then it's just going to march through both of those arrays and just copy the characters over until it hits the null character in the source. The string cat function is used to append the source string onto the end of an existing destination string. So if you already had some characters in the destination string, string cat will append the source characters onto the end of it. All of these functions are string handling functions, and so they will guarantee that there will be a null character sitting at the end of the string when it's done. Even if your string isn't long enough, it will just run off the end and then put the null character there, possibly overwriting something in memory. The string function is used to search for a smaller substring, which we call the needle here, in a larger string, the haystack. And you may have heard the, the idiom, searching for a needle in a haystack. And so the haystack is the large string and the needle is the thing you're looking for. What this does is it returns a pointer to the needle. So it gives you back the address of where it found the needle. And then string character, searches for a single character within a string. And actually, we wrote a function a whole lot like this, didn't we? Returns a pointer to the found character. The string compare function is used to compare two strings. It will returns 0 if the characters inside of string 1 are equal to the characters inside of string 2. So essentially, if those two strings are equal to each other, it'll return a negative number if S1 comes before S2, essentially alphabetically, and it will returns a positive number if S1 comes after S2. And then finally, the string length function returns the length of the string. And actually, we wrote a function a whole lot like this a week or two ago. So all of these functions work on existing strings. You have to have already had the memory allocated for them, whether that's a character array allocated on the stack or using something like malloc to allocate the actual characters for it. None of these functions will allocate a string for you. You have to do that work first. Also, none of these functions, as they are, will guard against overwriting a string. So if for example, for string copy, if the destination is shorter than the source, it'll just zip right past the end of the string and go into uncharted memory. Same thing for string cat. If the destination is not large enough to hold the existing destination plus the source, it'll just go right off the end. There are some equivalent versions of this. There is like string ncat, in which you give it a length and it will guarantee that it doesn't exceed that length. There's also string ncopy, in which you give it a length and it will stop when it hits that length. So almost all of these functions have an equivalent version where you pass in a length, and then it will stop at that length. But most of the ones that people learn about are the ones without that on there. String copy. What if source and destination overlap? I think then it is kind of implementation dependent. I think the definition for string copy does not say what it's supposed to do if the destination and the source overlap. So you may get kind of unpredictable results. And what he's talking about there is, let's say you have a source string, and in memory, you give it a destination where some of the bytes overlap. I've drawn them up on top of each other, but actually think of them as being like this, right? So some versions of string copy will behave kind of correctly in that it'll copy this one over here, and then this one goes here, and this one goes here, and then now you're going to get some kind of like, weird duplication, but still it'll behave correctly. But some string copies copy in reverse. So they may start by copying this byte over here, and this byte over here, and then this one over here, this one over here, and then you get really weird behavior if that happens. So I think the manual or the specification for string copy does not say what's supposed to happen if the memory overlaps. And so you get kind of unpredictable results. There is a function called memcopy, which I don't normally talk about. But in memcopy, the specification for that says specifically it will handle overlapping memory correctly. And so it'll do the copy so that it doesn't collide a whole bunch of stuff. But the string copy functions, I think, don't specify what happens in that case. Some chat about something called safe copy. I think what that, I'm just guessing, but I think the safe string copy ensures, I think, that it copies from the front end to the back end, and therefore it doesn't create this weird like overlap problem. I think. I'm guessing, actually. Okay, and then three more functions. One of them you already know about, fgetS. We've seen that before for getting input from the keyboard or from a file. And then finally, two more functions, one called A2I and A2L, that are used to convert strings into integers or longs as appropriate. Okay, so quick little program just to show you some of these. Let's call this strings.c. Let's just say we've got a first name and a last name, and we just want to put them together and make a full name out of that. So let's do 10 characters for that, and let me just put in my name there. And we've got last name. I'll put in my name, and then let's make a full name. Now I need to make sure that the size of full name is at least as long as the two names stuck together, and I'm going to want to put a space in between them. So I'm going to need like 5 plus 5 plus 1, that's 11, and then I need at least one more for the null character. So the full name has to be at least 12 characters long for the names I have here. So let's just go with 20 just to make sure. So in order to assemble the full name, I first need to take the first name and copy it into the full name. So string copy, destination comes first, and then my first name. And now how would I put the space after my first name? Now, those of you coming from Java are thinking, in Java this was really easy, right? I just use that plus thing and I can join strings together. But we can't do that in C. We got to do it with these string functions. So if we want to assemble a string out of some existing strings, we have to use string copy first to move the first string into place. So I've got first name, last name, and full name. So the first thing I need to do is make a copy of first name and put it down here. And now I want to make sure that there's a space in between my first name and my last name. So what function should I use?
The stir cat.
Good. There was a suggestion, maybe I should just use like the array notation. Maybe I should find the string length of first name and then just index into first name and stick a space there. That's not a good solution because that'll overwrite the null character that's there with a space, and now there's no longer a null character in my full name, and so my string functions won't work correctly anymore because they're looking for that null character to figure out where the string ends. So we're going to use string cat to move the space onto the end of the existing full name. And then we'll use string cat again to put my last name on the end. Maybe you got some appreciation now for all the work that goes on behind just using the plus in Java. You use the plus in Java, this is essentially what it's doing behind the scenes. Good, that looks good. I took the existing first name, last name, and assembled that into a full name with a space in between the two names. So now let's switch it up a little bit. Let's have it get input from the user and then greet the user with their first name and last name. So let's replace these with some print statements. What's your first name? And then we can use something like scanf to read in a string. And then we'll do last name. And then we'll assemble them together and we'll see if that works. Well, that seems to work just fine. Yes, string cat does instead, it stands for string concatenation. Concatenation means to stick two things together. But, you know, some people don't have a single name for their first name. They don't have a single name for their last name. Some people's first names are actually two names. Like, I don't know. So scanf here doesn't work correctly because it stops at the end of the first word. So I typed in two names here for my first name, and it took Stan as my first name and Lee as my last name. So it printed out the prompt for last name, but it didn't allow me to input anything because it goes, oh, I already see you typed in two words. I'll just put in Lee for the last name. So scanf is not the best tool for reading in multiple words. You can coerce it into reading multiple words in, but maybe a better tool here is to use fgetS for two reasons. One is it will allow us to input multiple words, and two is it'll stop if we input too many things. So let's replace this scanf with fgetS. And the other scanf with a call to fgetS. So now this works better. We input the first name, and we typed in two names. And let's put in the last name. And now it doesn't look so great, right? So the words come separated. What's going on there? Well, remember fgetS, unlike scanf, fgetS will leave the new line characters on the ends of the strings. When I press the enter key or the return key on my keyboard, that's an actual ASCII character that gets sent to the computer, and it gets put into the string as well. So fgetS is recommended over scanf because it will allow you to avoid these buffer overrun errors. We overrun the error, the buffer set aside for the string. Like I said, there is a way to coerce scanf in order to do that as well, but it's not like done by default. So the problem here is that fgetS puts the new line characters or leaves the new line characters on the strings, whereas scanf trims them off. Now remember, we wrote a function last week or the week before called trimNL that will trim the new line off of a character. And the way it worked was it scanned forward through the string, looking for the null character that was sitting on the end, or looking for the new line character that was sitting on the end, and then replaced that with a null character. Do you remember that from last time? So we can do that, but we could do it with the existing string functions. What we're going to do is use one of the functions to go find that new line character, and then use the return value from that to replace it with the null character. So which of these functions do you think we would use to go and find that new line character? Why don't we use this one here, the character finding one? So we'll use string character, strchr, we'll pass in the string we want to search for, and then also the character we want to search for. And we're going to put into single quotes the new line character because it's just one single character. And it's going to return to us a pointer to where that new line character is. So that pointer will come in the form of a character pointer. And then we just have to replace what that new line character is pointing at with the null character. And then we can do the same thing for the last name. Now I'm going to get an error when I compile this. We get a redefinition of NL on line 17. So this previous definition here is on line 12. And the reason for that is I can't declare two variables with the same name within the same function. Or I should say within the same scope. So the answer there is just remove the declaration for NL for the second one, because we're just going to recycle the same variable again. So this should now work. Oops, compile. Oh, now I'm thinking, I think I might have gotten these reversed. Let me just switch these around. Again, when I wrote up my notes there, I was really going off of memory. Oops. Was that it? No. Okay, now I need to look it up. What did I do wrong here? String character. Yeah, that's right. Character, the string to search for, and then the thing to search for. Yeah, okay. Incompatible pointer to integer conversion assigning to character from...
On line 17, you should remove that asterisk.
Yeah, I need to actually do it. You're right, right there. Because NL is already a pointer, and so I shouldn't be trying to dereference it. Okay, that fixed it. Whoa. That's strange. Let's try this again. Huh. What's going on there? Okay, I committed one of the mortal sins of programming. It's called a poisoned copy and paste. A poisoned copy and paste. And what that is you blindly copy and paste some code, and then you don't go over that code and go and make the changes you were supposed to make. You just copied it, and now it's poisoned because you haven't gone over and just verified that it's correct. What did I do here to poison the paste?
You didn't change the variable inside of the function call.
Yeah. So I'm now, I pasted in this string character search through first name. First name no longer contains a new line character, so it didn't find it. When it can't find the character you're looking for, the string character function returns a null. And then I try to dereference the null and assign it to the null character. You can't dereference a null pointer. You get a segmentation fault. That's a deliberate thing the computer does. If you try to dereference a null pointer, it crashes your program. In Java, you get a a null pointer exception. But in C, you get a hard crash. So this needs to be last name. So that was called a poison copy and paste. And now it works correctly. Well, almost correctly. And so there was a suggestion up in the chat, which was, why not just do something like this? This is something you can do here. This will actually work. So you're going to call string character, get the pointer to the new line character, dereference that pointer, and then assign it to be the null character. Okay, let's compile the program. Oh, and now it's complaining about the new line A variable doesn't exist because I took away the declaration for it. Okay, and that works fine. Okay, but I would actually encourage you not to do it this way for one primary reason. Let's put it back the way it was. And that reason is the string character function will return the pointer to the new line character, the first one that it finds, or it returns a null if it didn't find one. Now fgetS puts the new line character on the string. So this usually works, but it won't work if there's not a new line character there. If there's not a new line character there, when we try to dereference that null pointer, we get a crash. fgetS will not put the new line character on the end of the string if the user typed in more characters than the string can hold. So my string holds 10 characters. If I type in more than 10 characters, there will not be a new line character on the end of the string. Let's go ahead and save this, compile it. I'm going to run it, and I'm going to type in more than 10 characters. And then we get a crash because the string character function here returned a null. And when we try to dereference the null, we get a crash. Now, I'm going to show you two things. One is, what do you do about that? And two, how can we avoid that problem in the first place? Okay, so we're running out of time quickly here, so let me quickly show you something here, which is, how do you figure out where your program crashed? All we get here is a report that the program crashed, but we don't get any indication about where it crashed or what caused it. So when the program crashes, it takes a snapshot of your computer's memory at the moment that it crashed. And that snapshot is written to a file called core. This file contains a snapshot of the computer's memory at the moment that it crashed. So we can use our good friend GDB to figure out where it crashed. And this is the command line version of GDB we're going to use. So the first thing we have to do actually is recompile it with that -G flag on there. Otherwise, this is not going to work. And then we'll run the program again, and we'll type in something that's too long. And then it crashes. And now we're going to go GDB, the name of the program, a.out, and the name of the core file. And get past all this stuff here. And now it says the program terminated with segmentation fault at line 13. This is really useful information. If you can't get anything else out of GDB other than this, I'd say this is really important. Where did my program crash? GDB will tell you it crashed on line 13. We can look up here in line 13 and say that's when we were dereferencing this NL pointer and trying to assign a value to it. Now, if you want, you can say print out the value of NL, and it's 0, so the value is null. Okay, I'm going to type in quit to get out of this. So what did I do there? I compiled the program with the -G flag, and then I ran it as normal and let it crash. And then I typed in GDB, and the name of the program, and then core. And so it'll read in the core file, it'll read in the executable, correlate those two, and then tell you what line your program crashed on. We'll get into more of that a little bit later, but there's some other things you can do on the command line. Sometimes the program crashes in the middle of a function, like it crashes in the middle of printf. The reason for that could be you passed in some parameters that are incorrect. But you might want to find out, so it crashed in printf, but which one? And there's a way to find out like you can do what's called a backtrace, and you can print out all the functions. You can print out basically the call stack, and you can see all the functions that have been called, and you need to just roll it backwards until you find the function that has to do with your program, and that'll tell you where in your program it crashed. So the command to do that is called bt, backtrace, and it will show you your call stack. But we'll get a chance to show that to you later. But in the meantime, how do we fix this problem? How do we fix this problem where sometimes there's a null character, a new line character in the string, and sometimes there's not? So this is the way I would actually recommend you trim off the new line. Go ahead, call string character, get the pointer to the new line character, and then check to see if that the value of NL is not a null, then go ahead and dereference it and assign the null character to it. So check to see, does it have a valid value? If it does, then you can go ahead and dereference it. If it doesn't have a valid value, you're not going to dereference it, but that's okay. It means there wasn't a new line character on there. Do something over here. If NL, go ahead and dereference it. So that's why I recommend not just blindly assigning a null character to it, because there are those instances in which there's not a new line character, and your program will crash in that case if you just go ahead and assign to it. What we're essentially doing here is we're checking to see this is not equal to null. But remember, the value of null is 0. So we're saying, is NL not equal to 0? And then there's an implicit check to see if a value is not 0 by just giving the name of the variable itself. Is 0 the only invalid value that a pointer can have? No. I mean, if you try to dereference a null pointer, then you get a crash. But if you also try to dereference a pointer and it points into a segment of memory that you don't have access to, then you'll also get a crash. So if you got a pointer off to some address of memory that's not in one of your segments, then you can get a crash. You can also get a crash if you try to dereference into memory that has been deallocated by the memory allocator. So if you allocate some memory and then you free it up later and then you try to access it, it'll crash. So in that case, the value of the pointer isn't null, but it's invalid. What C does not have is the exception handling that Java has. So there's no way to do some kind of like try catch, where you can try to execute something and then catch the exception if it happens and then do something about it. So C will just crash your program. Actually, that's not true. There is exception handling, it's just really complicated to do. What you can do in C, and we probably won't have time to do this semester, but we'll see what happens. What happens here is when your program crashes, the operating system sends to your program something called a signal. You probably saw in the output here, it says, program terminated with signal, sig, S-E-G-V. So segmentation violation signal. So a signal is sent to your program by the operating system to indicate that something went wrong. Normally, when you receive a signal like that, the program crashes or stops. There are many signals. There's about 3 dozen or so. There's like when you press Control C to stop your program, that's called the terminate signal. So the shell receives the Control C, and then it sends the terminate signal to your program. And the default behavior when you receive the terminate signal is to just stop. There's segmentation violation. There's signals for illegal memory access. There's signals for illegal instructions. So if your executable contains code that can't be executed on the processor that you're running, then you'll receive an illegal instruction signal. And for most of these signals, the default behavior is to crash and then write out a core file. You can override that. You can put in your program a signal handler that says, when I receive this signal, here's some code that I should do. Like I said, the default behavior is to crash your program. But you could say, if I receive a terminate signal, I'm just going to ignore it. And I won't terminate. I'll just keep running. There are programs that do that. Right? They have valid reasons for doing that. So you could write a signal handler that says, when I receive a segmentation violation signal, I'm going to do something else instead. I won't crash. I'll just keep going. I'll ignore it. And so that's essentially what those exception handlers are in Java, is they're just signal handlers. But that's an advanced topic for now. We won't be able to get into it just yet. Okay, so as far as assignments go, there is an assignment already posted. It's a warm-up assignment. It's called, gosh, I don't remember what it's called, but you'll see it on there. And basically, it's a program that works entirely with these string handling functions. String copy, string cat, string character, right? It's just a program to just exercise the use of these functions. You have enough information right now to get started on that program. There's another program in there called command line arguments. We haven't introduced that yet. You can probably read about it in your book. But that's basically the same program again, but using command line arguments. So instead of getting input from the user, you're getting input right from the command line. So you're going to get a whole bunch of words on the command line and do stuff with it. We don't yet have quite enough information to get started on that if you're following along on the videos. But again, you can find that information in the book, and you can probably muster your way through it. So you should be able to start on that first program now. Let me see if I can go ahead and bring it up on the screen here. And then just as a reminder, there is no live stream on Thursday. So we will be back again next Tuesday. But let me bring up this assignment. Boy, we're scrolling way down now. Here it is. Okay, so the program should repeatedly prompt the user to enter a string of no more than 20 characters. The program will end when the user types in done in all caps. You use fgetS to get input from the user. Because fgetS puts the new line character on the end, you should trim it off. And I showed you a technique today about how to do that. The program will then use that input to build up a larger string, and that larger string can be no more than 1,000 characters. So if the input the user typed in is contained within that longer string, just ignore it. If the user input is less than the longer string, as indicated by the value returned by string compare, then you are going to prepend the input onto that longer string. You're going to put it up in the front. And if the input is greater than the longer string, you're going to put it on the end with a space. After each user input, display the longer string. So here's a sample run of this program. So the user types in hello, and then the longer string just becomes hello. The user types in world. Now world comes after hello, so it goes on the end. And they typed in bye. Now bye comes before hello world, so it comes on the beginning. Now cat is interesting. Cat comes after bye hello world, so it goes on the end. Okay, this is not as complicated as you think. We're not inserting cat into the middle. We're not sorting the words. We're just simply using string compare to decide whether the inputted word goes on the end or on the front. So cat comes after bye hello world, so it goes on the end. WORL is contained within the string, so it's ignored and nothing changes. See it so far? Okay, beep comes before bye hello world cat, and so it goes on the front. Bingo comes after beep by hello world cat, so it goes on the end. And then finally done, and then we're finished. Okay, so let me emphasize, the program is not putting the words in alphabetical order. It's just simply putting the words on the beginning or the end. You can do all of this with the string cat, string compare, string copy functions that we learned about today. You know how to append onto a string? How do you prepend? Well, there's no function to do that, so you're essentially going to have to make your own. Don't really have to, someone's suggesting, you don't really, says just keep track of the first character. But what if the word the person typed in was beer instead of, they already put in beep? Where would beer go? Would beer go in the beginning or in the end? So the string comparison functions are probably the easiest way to go about doing this. Yeah, so if they typed in beer, that would go on the end because R comes after P. So don't overthink this one too much. It's just a warm-up program. Is there a reverse string function? I don't believe there is. But we don't need to do that for this one. There's no reverse string. But prepend, how would you prepend? Well, there is no prepend function. So you're going to have to do something like copy the long string off into a temporary string and then put the new word up at the beginning and then put the other word thing on the end. So you're going to have to use the built-in functions to do that. So prepend is not just a straightforward like string prepend function. Maybe you could write your own. It's just a combination of string copy and string cat and so forth. Okay, so with the information you have now, you should be able to do this program. The next version of the program we write works the same way, but the words come off the command line. So you type in the name of the program and then your words here, and then it just shows you the string being assembled as it runs. So you're going to turn in this program using Git and Bitbucket. So I showed you last time how to create a new repository, initialize a repository, push it up to Bitbucket, and then you'll turn in both the programs in one repository. And then I'll take a look at them. Okay. There's a lot of stuff today. Hopefully you got something about that debugging session. All right. Well, we ran a little over time, but I think that's okay. Any questions, Chris?
No questions. But that
Okay.
was great about the debugging and going through all the string functions.
Good. And what a bizarre little bug that was.
Yeah, that was neat. I like encountering bugs like that because once you go through it, you're gonna remember it for a really long time.
Yeah.
Once you go through the work of having to figure it out, then I find that it is more memorable.
And back when the student first introduced that bug to me, I was like, that is really weird. And I didn't know what was going on at first because everything looks fine, right? It compiles fine. What the student noticed was if you rearrange the order of the variables, it suddenly works fine. Right? Remember how those variables were laid out?
Yeah, because it changes their order in memory.
Yeah, or if you insert a new variable. So I think what happened is they'd actually inserted a new variable in there, kind of a debugging variable, a flag, and that had the effect of pushing these variables apart by enough so that the problem didn't exhibit itself. And so I said, well, that's really strange that if you add a variable, suddenly it works correctly. If you take that variable away, it doesn't work. And so that, to me, it was like, oh, this has something to do with the computer's memory. It has something to do with the way the variables are being organized in memory. And I had to like draw a picture like I've shown here to see what was going on. Because again, it didn't really initially register that the problem was the string was too long, because everything looked okay. And then I remembered, oh, there's a null character on the end. The question is, you have a question on GDB. Can we make a loop stop at a certain iteration? Yeah, you can. You can set a breakpoint based on an expression. So if I did something like, oh, first, let me stop this debugging over here. Let's see, let's set a break on line 15, like we did before. And then we can run the program, and it will stop at line 15. And there I can do things like P for print. Instead of the word print, I can just use P. I can see the value of end. I can see the value of start. I can see the value of image. But then I can do things like I can say break. I think when break, I can say when break is start is greater than 1,000. No, let's do 5,000. No. No, I don't remember. Let's see. Help breakpoints. Set a watch point for an expression. Watch. Start greater than 5,000. And then I can say continue running. Let's remove the breakpoint on line 15. So let's see, how do I delete a breakpoint? I guess it's delete. Delete 15? No. Delete breakpoint number 1. Continue. Okay, so I said continue, and now it just starts running. It just continuously runs, and now it's stopped when the value of start exceeded 5,000. So if I print the value of start, we can see it's now 5,500. So you can do the same thing over here. You can do these watch expressions. Start greater than 5,000, same thing. And then when the value of start exceeds 5,000, the program will stop. Oh, let's remove this. And let's stop debugging, start debugging. Did it do it? No. I guess, is it a breakpoint? Add function breakpoint, no. Oh, maybe what I have to do is I should get it to at least stop first. Then we'll run it. It starts here. Let's remove this one. Did it do it? I'm going to have to do a little bit of research. But that's basically how you do it, is you can set up a watch. And then when that condition becomes true, then it stops the program. But I need to do a little research. But you saw how to do it from the command line. You can say watch start greater than 5,000. And let me see, does that do it? No. All right, back to do some more research. Oh, every time you run GDB, is there a way you can save your breakpoints? Oh, there's got to be a way to do that. Like have the breakpoints set in some kind of file so that you can just load them all in. Here, look, save breakpoints right there. Whoa, stop that. Save breakpoints as a script. Oh, I missed it. Can you see it right there? There we go. Save breakpoints. Save. Probably need to give it a file name. But yeah, you can. You can basically save your GDB configuration, and then you can just load that in so that every time you run or every time you start the debugging, it starts with that same configuration. So it can be done. So whenever you're using the graphical debugger over here, behind the scenes, it's just sending those command line options, command line commands to the GDB backend. So this is just a pretty little interface on top of typing in the commands. I learned to do debugging entirely from the command line. This user interface stuff here, this is a little strange to me personally because I learned to do it on the command line. So that's why I'm a little flummoxed sometimes when I'm using the graphical one and I don't quite know what to do because that's not the way I learned it.
Going back to what you were trying to do earlier, stopping or breakpointing when the variable is greater than a certain value.
Yep.
When you're setting your breakpoint, you can actually right click and there's an add conditional breakpoint choice.
Here?
So,
or
right.
Here? Where did I right click?
Yeah, so where you have the red dots.
Uh-huh.
When you're setting a new breakpoint, if you right click.
Oh, here we go, add conditional breakpoint.
There you go.
Okay, so it set it down here. So yeah, so it should now have stopped, right? Oh, I set the breakpoint up here when start is greater than 5,000. It will never be greater than 5,000 here on line 11. I have to do it inside of, is that right? Do I have to do it inside of here? Yeah, so this is a conditional breakpoint when start is greater than 5,000 here, but it will never be greater than 5,000 at this point. So let's set it maybe here. Add conditional start greater than 5,000. Now we'll run the program. And good, now it's stopped when the value of start is 5,500. Good, thank you. That's what we wanted. Okay, well, I learned something today about the debugger. Thank you for that. No, GDB is not the only C debugger. It's the one that I happen to know how to use. There's one also called LLDB, which can be used for your programs as well. It works. Again, I learned GDB, so I know the commands well enough to get by. LLDB confounds me sometimes because its set of commands are different. Like for instance, with LLDB, as far as I know, the last time I tried it, there's no easy way to tell it. Just tell me when my program crashed. Right? With GDB, you give it the name of the program, name of the core file, boom, it just tells you the answer. With LLDB, it was like you run LLDB, you have to load in the executable, load in the core file, tie them together, and then it will tell you. And it's like, that's just too much trouble. I just want to know where my program crashed. And so GDB tells me that information right up front. That's useful for me. Okay, let's wrap it up right now. Again, on Thursday, there will be no live stream. But tomorrow, we'll do discrete structures, and we'll be talking more about hashing. It'll be a great class, because I'll show you how to crack passwords. And you know what? In this C class, we're going to do that too. We're going to be writing programs coming up here in the next couple of weeks that will be used to crack passwords, except that instead of using some programs that someone else wrote, you're going to write your own. And I'll show you how that gets done. So by the end of this unit on cracking passwords, you'll be able to read in a dictionary of 2 or 3 million potential words, and then read in also a whole bunch of hashes that you want to crack, and then just in a fraction of a second, it'll do all of them. Okay. So there was a question about mutable versus immutable strings. Why don't we leave that for later? That will be a great question to ask later on, because there are, in fact, immutable strings in C, and it's a whole lot of fun when you try to change them. Because you don't know why it crashed. It crashed, I don't know why. Because there's no syntactical difference between the two of them. Right? They just appear, one just happens to be immutable and one happens to be changeable. But there's no difference in the way you kind of access them that tells you that one is immutable and one's not. Okay, so the question also is, when we get to the fork and threading, I'm not sure. Towards the end of the semester, if we do that. We got a lot of stuff to cover. So we'll see what we get to. Okay, take care of you all.
All right, thank you. Bye.
Bye-bye. Yeah, we've only got 16 weeks in the semester, so we can't necessarily get to everything we want to. You know, I do need to cover these data structures. Networking is always very popular, so we end up doing that. Forking and threading, we may not have time to be able to do that. I can at least maybe show an example of it, but it's kind of difficult to come up with an actual program that uses it. I have, in the past, done it with the password cracking, where we split up the work amongst multiple processors in order to potentially crack the files faster, to crack the passwords faster. The problem is, on our virtual machines, we only have one virtual processor, so when we do that, it doesn't give us any performance gain at all. So again, I could probably show an example of it, but as far as something useful to do, it's a little trickier to do. Okay, so I will end it here, and I'll see some of you on Wednesday. Otherwise, next week. Have a great day. Take care, and bye-bye.